Hello, everyone, and good morning. My name is Nathan Burns, and I worked under Dr. Helen Haynes over the summer, working on the EPIC detector, quality assurance, and improvements of the civil on-pilot design. Now, my talk will have three different parts on the EIC quality assurance with SR90 and improving light yield. But first, we're going to start with the EIC. The Electron Ion Collider, or the EIC, aims to have construction finished by about 2030. It aims to answer the questions listed here, such as, what are the inner structure of quarks and gluons, aka the particles that live inside of protons and neutrons? Why does gluon saturation in the color glass condensate occur at high enough energy? As pictured here, when you get higher and higher in energy, more and more gluons seemingly appear inside of these protons and neutrons. Where does the spin of the proton come from, and why are these quarks and gluons confined within their own particle? All of these are questions we hope to answer with the construction of the EIC. Pictured here is the actual schematic for the EIC. We have electrons coming in from this direction, the blue tube, and ions or protons coming in from this direction in the yellow tube. However, we'll be looking at this right here, located at interaction point 6, or IP6, the EPIC detector. The EPIC detector, as part of it is pictured here, is actually made up of 26 subsystems and is the general detector for the EIC. But our focus today is not on the entirety of the EPIC detector. We'll be focusing on the LFH cow, pictured right there. Now, the LFH cow, or the longitudinally segmented forward hadronic calorimeter, no, it's a mouthful, but I'll break it down for you, sits in the hadron going position and is made up of 600,000 tiles. Longitudinally means that it is segmented in the Z direction, segmented meaning it is separated by steel plates to cause hadronic showers, forward because it is in the forward position or hadronic going position, and calorimeter because it measures energy of particles. Now you might be wondering, how is it measuring energy of particles? Well, that is with the SIPM technology, coupled with scintillating tiles. How SIPM on tile technology works is that particles deposit energy into the tiles. These particles excite the atoms inside of the tiles, and when the electrons become de-excited, they go down in an orbital level. This causes a release of photons. These photons then bounce around inside of the tile and are reflected by an ESR wrapping that reflects, I believe it is 99% of light. Once it is reflected enough, it lands in this dimple where the silicon photomultiplier sits, and the silicon photomultiplier turns those photons into electrical signals. However, what kind of particles are we going to be hitting our scintillating tile with today? I'm so glad you asked. The first thing we're going to be looking at are cosmic rays. Cosmic rays are from the sun and actually also supernovas that interact with our atmosphere and turn into various particles. What we're going to be looking at are pions that decay into muons. These muons have a lifespan of, I believe it is about 25 nanoseconds, but they travel extremely fast and are able to reach the surface of the Earth from about 14 kilometers up. But they are important because they are minimally ionizing, meaning they deposit roughly the same amount of energy every time. We will also be looking at a strontium-90 source. Pictured here is the actual source from our lab. Strontium-90 has two different decay chains, one to turn into yttrium-90, which then decays again via beta emission. The beta particles are what allows for scintillation inside of our tiles. Now, the silicon photomultiplier we'll be using is the Hamamatsu S141601315 brand, which is the same kind of silicon photomultiplier being used in the EPIC detector. We will then be reading it out with a Kind DT5202 digitizer, which goes to a Janus reading in a FIRS 5200 readout. Now that we have finished with the background, we can actually move on to the actual quality assurance with SR90. Pictured here is the setup that we did. The point of this run, the quality assurance, is to test the light yield of the tile. In order to do this, we constructed this setup here with two tiles. One that is an actual test tile on top, and one that is called a trigger tile on bottom. We have a coincidence or majority trigger of 2, meaning that we can only read out data on the top tile if both the top and the bottom tile are hit, ensuring that we are only getting readings from the strontium-90. However, we also had a translational stage, which moves in both the X and Y directions. But anytime that we have a new translational stage, we have to have a new graphical user interface, or GUI. This was the GUI that I came up with, that I coded. We have sections for manual control up at the top. We have recalibration and origin testing, and then we have the actual testing buttons down here at the bottom. You'll notice down here we have an actual grid that tells you what step of the tile it is currently on. Oh, okay. What step of the tile it is currently on, as well as a graphing window over here that enables for immediate graphing of the tile the second that you are done with the run. You'll notice you can segment the tile into a 2x2, 3x3, 4x4, or 5x5 matrix, and you can input the gain of the SIPM. Now, you might be wondering, what is the gain of the SIPM? Well, I'm so glad you asked. The gain of the SIPM is what allows us to turn ADC, which is analog to digital converter or arbitrary units, into photoelectrons or PE values. These are non-arbitrary units and are much easier to digest in things like conferences. So in order to get SPS data, which enables us to get the gain, you have to bombard the SIPM with an LED pulsar. This gives you the graph above with individual photon peaks that are just n photons and then n+1, n+2, n+3 photons. This Landau Gaussian distribution is fitted to the troughs of the peaks and is then subtracted away as background noise. And then you take a fit of this to Gaussian distribution and subtract between the two of them to get the gain value. Lastly, this was the actual data we got from a 15-minute per section run, which was approximately 6.25 hours. We have plans to run for about an hour on each section for 25 hours. What you'll notice already, the light yield looks extremely consistent among the tiles, roughly 20 PE or 20 to 21 PE across the tile. However, you'll notice even more consistent is if I zoom in the center of the tile. Among here, my PE values only range from about 19.75 to 20.16, extremely close together. So preliminarily, the light yield is extremely consistent. However, some things were not. And the reason we are worried about the center of the tile is because the tile is actually wrapped in ESR. When the tile is wrapped in ESR, the edges of the tile over here are actually need to be slightly cut in order to fold over the tile. These can cause light leaks, and these light leaks cause for incorrect counting statistics. In the counting statistics, you'll notice that the edges of the tile, specifically the corners, were extremely low in counts compared to the middle of the tile. About 26,000 compared to only 1,500. That's a really big difference. So this brought about the question, what is the beam width that we are actually hitting our tile with? Are we perhaps overflowing the tile with too much data? So we decided to characterize the beam. Yes, simulations were characterized as the beam. Two methods were performed and analysis was done in Mathematica. The first method was to fit each row and column of the Gaussian of the data to a Gaussian distribution and extrapolate to find the standard deviation. The amplitude was then found via this equation, and then you could make a simulated data to see if you could match if your model could correctly match the data. Pictured here are the actual Gaussian fits along the row. You actually notice that the one row is actually different from the other row in terms of the peak values. One is much higher than the other. We actually already knew this would happen because the tile was not uniform in length and width. So this is actually reassuring that they are slightly different. However, from this, we were able to get a Gaussian fit that looks approximately like this. You can compare it to the original data. It's close, but it's not perfect, especially among the inner region, which we actually care about. 21,000 compared to about 14,000, not the best. So we moved on to method 2. We gave Mathematica the entire data set and let it vary the parameters itself and find one that minimizes the sum of squared residuals via this error function equation. This error function equation is actually just an integrated Gaussian across the entire width of the tile. And Mathematica gave back these values. You'll notice, once again, that as we assumed with the Gaussian distribution, the center is not perfect. It is very close in the x direction, as we could see with those previous data, but it was a little bit far off in the y direction. The sigma, however, is exactly the same. This Gaussian fit was much better compared to the other one. You'll notice only 12,000 to 14,000, 60,000 to 17,000. Much better, especially among the center. Lastly, we're going to look at Jesse's work, who is a high schooler that helped us. Previous data has shown that the MPV value between molded and machine tiles has shifted slightly with another undergrad named Langdon. So we had the question, can we prove the molded tiles to be as good as machine tiles? To do this, we decided to place ESR foil around the PCB board where the silicon photomultiplier actually sits to see if we could actually reflect these photons back into the silicon photomultiplier. It was not, the setup that we did for this was cosmic data. So we had 4 tiles set in a coincidence, and the data analysis was actually performed by Jesse himself. Lastly, we have some success. It is possible that this will work. We had a lot earlier success, but it's possible that was attributed to error. As you can see, these graphs are incredibly similar with about only a PE of increase. So, well, evidently, I don't have any conclusions, unfortunately. I'm not sure what has happened here, but you can take nothing away from this talk is the grandiose thing. However, no, we have in fact done quite a bit. The tiles, the light yield was quite uniform. We were able to characterize the strontium beam, and we have promising work with the high school. And lastly, I'd like to thank the following people for the assistance they have provided me with this. Thank you so much. Yes, that's a great question. So we're looking for something called granularity. Granularity enables us to see how like precise in the fluctuation of values we have. We don't want extremely high granularity because that can cause to like more and more errors introduced to the system. We might see things that aren't actually there, right? Hence the reason why we actually don't want to wrap this ESR foil around machine tiles, right? Because they're already so high in NPV value that we don't really care that they're high enough, that they go higher, right? However, we have an NPV value of 13 versus 20, 21. That means that I'm literally reading 7 less photons than I could be reading. That's quite a bit of data loss that I could have. So if we can get that value up, then we can replace the machine tiles with molded tiles. And that is a huge benefit because machine tiles cost $25 a tile and molded only costs 25 cents. So we're talking, and when 600,000 tiles in a detector, we're talking orders of magnitude of like millions of dollars.